Okay, this is sample problem 1613. Determine the pH and percent ionization for acetic acid solutions at 25 degrees C with concentrations of A 0.15 molar, B 0.015 molar, and C 0.0015 molar. Okay, so this is acetic acid. So if we look in table 16.5, I think is the table. Let me actually check. Table 16.6, sorry. So you look in table 16.6, and you want to look up acetic acid. So acetic acid is CH3, COOH, and it has a Ka value of 1.8 times 10 to the minus 5. Okay, so this is a relatively standard problem. We're just going to find the pH and the percent ionization at different concentrations. So let's begin the first one. We're going to add water. Oops. Acetic acid is the acid, so it donates CH+. Sometimes you may see me put the hydronium first and then the conjugate base, but this time I put the conjugate base first and then the hydronium. Doesn't really matter. Okay. For part A, the concentration is 0.15. The initial concentrations of the acetate and hydronium are 0. Q is 0, so the reaction goes to the right. And so at equilibrium we have 0.15 minus x, x and x. The expression for Ka is the concentration of acetate, which is x, times the concentration of hydronium, which is also x, divided by the concentration of acetic acid. Let's go ahead and use our assumption here that this is x squared over the initial concentration. Okay. Now, we have a value here. We have a value that is equal to 1.8 times 10 to the minus 5. So solving for x, x squared would be 0.15 times 1.8 times 10 to the minus 5. So let's figure out what that is. .15 times 1.8 times 10 to the minus 5. Okay, so that's 2.7 times 10 to the minus 6. So x would be the square root of that. Looks like it's 1.6 times 10 to the minus 3. Since x is the same thing as the hydronium concentration at equilibrium, the pH would be the negative log of that. Log base 10 times negative 1, 2.78. If we want to find the percent ionization, that's the concentration of hydronium divided by the initial concentration of the acid times 100. So that would be 1.6 times 10 to the minus 3 over 0.15 times 100, which is equal to 1.6 times 10 to the minus 1 over 0.15, which is 0.16 over 0.15. A little bit more than 1%. .06, about 1.1%. Of course, that also serves as a test to see if this was a good assumption that 0.15 minus x is approximately equal to 0.15. The fact that we got less than 5% ionization means that it was a good assumption. So all we would need to do in part B and part C is change the initial concentration. So instead of putting 0.15 here, we'd put 0.015 here, and here, and here. That would change this value to 2.7 times 10 to the minus 7. So then we would take the square root of 2.7 times 10 to the minus 7, and then we'd take the negative log of that. Okay, so for part B, finding the pH, we would first say that x is the square root of 2.7 times 10 to the minus 7. We knocked it down by a factor of 10. Take the square root of that. That would give us 5.2 times 10 to the minus 4. Okay, so now the pH would be the negative log of that. Take the log of that times minus 1, 3.28. So look what happened. By decreasing the concentration to 0.015, the pH, instead of being 2.78, became 3.28. But take a look at what happens in part B to the percent ionization. It would be 5.2 times 10 to the minus 4 divided by 0.015. Right? It's divided by the initial concentration. So 5.2 times 10 to the minus 4 over 0.015. Times 100. 3.47%. Look what happened to the percent ionization. It went up to 3.5. Okay? So that's one finding, is that as you lower the initial concentration of the acid, the pH may not be as low, but the percent ionization does go up. Okay? So now what about part C? In part C, we would be changing the initial concentration to 0.0015. Right? Let me see if we can get a little more room here. So in part C, x would be the square root of 2.7 times 10 to the minus 8. (1.64 times 10 to the minus 4). So the pH would be the negative log of that. So negative log 3.78. So again, lower the initial concentration of the acid, it becomes less acidic. That makes sense, right? Like if you have less acid, it should be less acidic. So every time we knock down the concentration by a factor of 10, the pH goes up some amount. So we started off at 2.78, then we went to 3.28. Now we're all the way up to 3.78. What about the percent ionization for this part? Well, that would be the X divided by the initial concentration times 100. So 1.64 times 10 to the negative 4 divided by 1.5 times 10 to the minus 3. Times 100. Look, it went all the way up to almost 11%, 10.9%. Right? So again, pattern holds. As you lower the initial concentration of the acid, the pH is higher, but the percent ionization does go up. More of the acid, it reacts in there.